Guten Morgen. All right, today we're going to start our third section of the book out of like 18 sections or something crazy like that. But this is a big one, very important. Functions. Functions are like a major part of algebra. You need to deal with x and y, and guess what? Almost all of the equations you learn with x and y are functions. And so we need to know what those are. And that's what this chapter is about. I'm going to call it a chapter because I've been teaching out of books for a long time. So let's share our screen and get started. This one should hopefully be a pretty fast one. Wait, that'll work. And I'm going to go to here, and you should be able to see our textbook. All right, so we're going to buy some refreshments because that sounds like a great idea. Look at these two beverage vending machines. Users press one of 6 buttons, A, B, C, D, E, or F, to get a drink. That inputs a code, but that's just confusing. Really, you push a button and you get a drink. We'll talk about the details in a second. The two machines have the same 6 beverages, but they are loaded differently. Play an animation to see the action of the two vending machines. Okay. In a refreshments vending machine, the beverage containers are not intermingled or mixed together. Okay, we'll see what that means. So let's push this here. I'm going to make that small. Here we are. We're going to push this button and we're going to see what happens. Oh, if you push A, you get orange juice. Brilliant. That makes sense. What if I push B? I get apple juice. If I push C, I get skim milk. If I push D, I also get skim milk. If I push E, I get chocolate milk. And I push F, I get water. So that's the refreshments one. Seems useful. Okay, so that's our first one. This means each code, each button that I push delivers one unique thing. Well, you might argue with the word unique because notice C and D both give me skim milk. But still, they're using unique badly, I would say. But that's okay. You're right if you want to argue about that. But so let's ignore the thing unique. Let's say if I push a button, I always get the same thing out. So if I push C, I always get skim milk out. If I push D, I always get skim milk out. So depending on what I push, what I choose, my choice of what button I push always gives me the same thing. So I would never push A and get apple juice or skim milk or chocolate milk. But I will always get orange juice. Every single time I push A, I get orange juice. That is a dependable situation. All right, moving on to the next one. I'm going to push play again. We're at the cold drinks. Look, that one gives me orange juice as well when I push A. And if I push B, I get apple juice as well. This is really exciting. What's going to happen next? If I push B, I get skim milk. Did you see that? I can't go back. If I push C, I also get skim milk. If I push D, I get chocolate milk. If I push E, I get water. And if I push F, I get more water. Okay, so notice I pushed A. Every time I pushed A, I got orange juice. Some of the time when I pushed B, I got apple juice. Some of the time when I pushed B, I got skim milk. C, when I pushed it, I got skim milk. D, I got chocolate milk. E and F, if I pushed E, I got water. If I pushed F, I got water. So that's what happened with machine B. Okay, I'm gonna go back up here. It says every time you press B in the refreshments, you get the same thing. You get apple juice. What will happen when you press B in the cold drinks machine on the right? That's the big question here. And this is the question at the crux of what it means to be a function. So the way I like to think of it is functions are dependable. So if I go to the machine on the left, I can depend. If I push a button, I can trust what I'm going to get out. Even if I push C or D, I know no matter which one I push, I'm going to get skim milk. However, the cold drinks one over here on the right, I cannot depend on all of the buttons. Yes, sure, if I push A, I get orange juice, and if I push C, I get skim milk, and I push D, I get chocolate. And if I push F or E, I get water. However, B, if I push it, I might get apple juice, and I might get skim milk. I can't trust this machine. It's going to give me a surprise, possibly, and that is what makes something not a function. So we're going to talk about that more in this chapter. But basically, a function is something where you input, and in math, it's going to be a number. So we'll say input a number, like that's usually x. So if I plug something in and I do the math, I'm going to get something out. And every time I plug that same number in for x, I'm going to get the same thing out for y. So that's where we're going in this thing. Now, there are situations in math where I could plug the same thing in and I get two different answers out, just like the machine on the right here. And so we're going to be doing this type of situation. Refreshments is a function because I can trust that every time I push a button, I'll get the same thing out if I push the same button. But cold drinks is not a function because if I push the same button, I might get one of two different things. I can't really count on it being the same every time. All right, so we're going to look at the next page. What does this look like? The refreshments one, an example of a function, and I've talked about this. A function is a relationship between two sets in which an element of one set is associated with a unique element of the other. Now they're talking about using unique in a mathematical way, so it makes more sense. In other words, every time that I plug something in or choose a certain button or whatever the input is, if I do the same input the same way, I should get the same thing out. That's what it means to have an element from one set is associated with a unique element from the other. Ugh, that bothers me, but that's okay. All right, language note. Sometimes people go, oh yes, function is a weird word, so we might as well talk about this because it's used a lot of ways. When we say function, sometimes we are talking about what people do. Like sometimes people call a job or a role they have their function. His function is to greet people at the door. That's what they do. Some people use the word function when they talk about social events. So I'm going to a social function. Other people might use the word function to describe something that is working correctly. This machine functions normally. Actually, this is really close to the way that math uses it. Not quite the same. In this topic, you learn about mathematical functions. So mathematical functions are a relationship between two sets. And I hope that this is good. We're going to explain what sets are later. But the important thing is their relationship. We're going to talk about how machines functions and math functions are very similar, actually. Okay, because these are machines. And they're very good for modeling functions. Now notice up here, questions 1 or 2, you might as well go in and look at them. Here's the assignment. Let's fill it out. Why does refreshments vending machine represent a function? So here's the deal. Every time I push the same button, I will get the same drink. That's why. Just so you understand, this right here on the left side is what we would call our input. And this would be our output. I'm going to go back a little bit and center this a little bit better so it looks nice. Okay, so the first half of the sentence, every time I push the same button, that's my input. Every time I do something, tell the machine something, it will respond the same way. And it says, why do the cold drinks not represent a function? Well, this one, if I push the same button twice, B, because that's the one, if I push B, might get 2 different drinks. I'm going to make the same capitalized. I know, but I'm just trying to make sure that you understand the way I would say it. Because what we're saying is when I push the same button twice, when I have the same input, I might get 2 different drinks. Okay, so if I do the same thing, I might have 2 different outcomes. That is a undependable situation. And in functions, we're trying to set up dependable situations, things you can always count on. That is kind of what a function is when you really think about it. Okay, 3 other examples of functions. I'm going to make sure we don't have anything else here. Page 3. The refreshment vending machine represents a function because the type of beverage you get depends on the code you press. Why do they use code? Oh well. Each input, the code, is associated with only one unique output, the type of beverage. The cold drinks vending machine does not represent a function. Either each input is not associated with one unique output. All right, which is what we just said. So if I push a button, I will always get the same thing out. Even if C and D give me the same thing as each other, they're still dependable. But on the second one, B is not dependable. It will give me apple juice or skim milk, and I want one or the other. I don't want the machine to choose for me. I want to be able to pick based on what button I push. That's the difference between a function and a non-function. Okay, the vending machine is only one illustration of functional relationship. You may have seen more every day. Here are some examples of functional relationships you've seen so far. They're giving some examples right here. I thought we were going to have to make up our own. So what do we realize over here? Well, the height of a baseball depends on, is a function of the amount of time since the baseball was thrown. So if you tell me how much time has gone by, remember that, I can tell you how high the ball is in the air. At 0.6 seconds, I believe it was at 12 feet. At 0.9, it was at 16 feet. So I give you a time, you can tell me how high it is in the air. That is a function. The height is a function of time. This one, we had the number of $8 pizza depends on how much money you have. So if I pay, they're $8 pizzas, so if I pay $24, I can get 3 pizzas every time. I don't pay $24 and sometimes I get 3 and sometimes I get 15 pizzas. No, the amount of pizzas always depends on how much you pay. It doesn't change. So that's a function. The number of pizzas I buy is a function of how much money I spend. Here we have the number of 1-foot squares on the border of a square pool depends on, it's a function of the length of the side of pool. Okay, so if I make the length 3 feet by 3 feet, we found out that 16 tiles go around the outside. 3 feet by 3 feet pool. If I have another 3 foot by 3 foot pool, it won't have 25 tiles that go around it. No, every time I have a 3 by 3 foot pool, it's always going to be 16 tiles. That is a function because it doesn't change based on the same input. The input is the size of the pool, and that size of pool always has 16 tiles around it every single time. So it's a function, it's a dependable situation where I tell you the size of the pool and the answer for that size will always be the same. I tell you how much money I have, the number of pizzas I can buy will always be the same. I tell you how much time has gone by, and you can tell me always that the height is going to be the same for that amount of time. So those are all functions. Functions play a major role in describing relationships mathematically in order to predict behavior. By the way, this is the third problem. So I'm not going to type it in, but I'm going to say baseball. You're going to have to write more than this, please. You can also think of your own. I don't mind that. Pizza. And the third one was tiles. I'll tell you a third one. I'm going to say computers. When I type the key for, we'll go with J, will always result in me having a J. It does not switch to other letters every time I press it. Same input always yields the same output. So that, see, that is a function. So that is a function. That's what we're doing. You've got to do that with baseball, pizza, and tiles. I said it out loud in words. I want you to type it in your own words. In your own words, describe what it means for a relationship between two variables to be a function. So we'll use the variables x and y. So x and y are the variables. So if you're talking about two variables, you can say x and y, and I'll know what you mean. So what does it mean for x and y? Remember, we always use x as our input. We use y as our output. That's just tradition. So think about all that we've been talking about. And think, what does it mean for x and y to be in a function? Two variables are in a function. Now, actually, you can use it in mathematical language, but I've just been thinking about this, and this might actually be a confusing way to do it. Control Z. You can also say, like, oh, I don't know, two other variables like height and weight are variables as well. So you could also say something like that, or height of a ball in the air, or whatever else. You need to explain what makes those two variables be a function. And I'll tell you, height and weight are not a good example of a function. So maybe we'll talk about, oh, I don't know, speed and distance. Those are good. Or time and distance, that doesn't matter. Okay, our variables. So if you have a certain speed and a certain distance, can you count? Can you count on, say I go at a certain speed for 10 hours, can I count on going a certain distance? Will it change if I don't change the speed? Think about those things. So we're just looking at, if I can count on the first thing, if I can say that the first thing's gonna stay the same, does that mean I can count on the second thing also staying the same? Does one change without the other? All right, so think about that, and we'll get back to that later, but I don't want to tell you the answer for the last one because it does say in your own words after all. So that's all the help I'm giving you. Good luck, have a wonderful day, and come back to class with questions. All right, thanks, and adios.